Hi there, this is Ms. Page and welcome. In this lesson we're going to be talking about how we verify trigonometric identities. Verifying a trig identity is different from solving an equation. In fact, many of the things that we do to solve equations we can't do in verifying trig identities. Just to give you an idea, identities are expressions or statements, really, equations that are true for all values of the domain of the variable. We don't solve for the variable. What we do is we transform one or both sides of the equation into an expression until they're the same. And then basically what we've done is prove that the left side and the right side are equivalent to each other, and then we can use it to do substitutions in other types of problems. So like our Pythagorean identities are identities. If we wanted to, we could say replace sine squared with 1 minus cosine squared, or vice versa. And so that's what we're looking at verifying, and then we prove them to be true. So you want to make sure that you understand you can't use your undoing algebra like you do when you solve an equation. That's what this is saying. When verifying identities, you can't add to both sides or subtract from both sides. You can't multiply or divide both sides by something. You can't square both sides or square root both sides. You have to work with just one side of the equation at a time. It can often be easier to transform the more complicated side into the simpler side. Sometimes we work with both sides, but this is a good strategy to try first. Look for opportunities to factor expressions using like a binomial structure with a GCF or a difference of squares, a trinomial that you think you could factor into two binomials. If you've got fractions that are being added or subtracted, combine them using the procedures that we've talked about previously. If you've got multiplication involved, remove the parentheses using your distributive property. Create a monomial denominator. I'll talk more about that one in an example. Look for opportunities to use your fundamental identities. Those are your quotient identities, reciprocal identities, and your Pythagorean identities. If you have things like sine squared, cosine squared, tangent squared, and so on, look at your Pythagorean identities especially. If that doesn't seem to be working, you can try turning everything into terms of sines and cosines, but always try something. Even if it doesn't seem to be working or you know it's not working, it can give you insight into other things to try. This right here is for the reference for the identities. I do not have, you've got your Pythagorean identities, quotient identities, and reciprocal identities, all of which are part of our fundamental identities. I don't have the alternate forms. You have those in previous notes. All right, so you'll notice that in your guided notes you have a strategy and then a line after it. So what I'd like you to do is state or write down what strategy we're using in this particular problem, working with the more complicated side. What we're going to do is take the more complicated side and transform it into the simpler side. And the more complicated side, I hope you recognize, is our ratio here. So one of the things that we can look at trying is when we see something like a secant squared theta minus 1 is looking at a Pythagorean identity and see if there is a substitution that we can make. It might be an alternate form of the identity, lots of times it is, but here's my one that involves secant squared. And notice if I subtract 1 from both sides, then I get tangent squared equals that secant squared theta minus 1. And this is what I have, so I can substitute with tangent squared theta, being an identity. They're equivalent. So this I can turn in this portion right here, I can turn into tangent squared theta. That's still over secant squared theta. And I'm just going to leave sine squared theta alone. Now, with tangent squared and secant squared, one of the things you might consider trying is thinking of this as, since tangent squared is in the numerator, this would be tangent squared theta over 1 times 1 over secant squared theta. And then using a quotient identity on our tangent squared. So we know tangent is sine over cosine. So you can do powers of tangent, and then it becomes powers of sine over cosine. So tangent squared theta becomes sine squared theta over cosine squared theta. And secant is the reciprocal of cosine. So if we have 1 over secant squared, then that becomes cosine squared over 1. So notice it flips and becomes the reciprocal function, still leaving sine squared by itself. So now we have a product, and here, since we're just working with this one side over here on the left, we are allowed to simplify that left side. So cosine squared and cosine squared will reduce to 1, and then we have sine squared over 1, which is sine squared. So we get sine squared theta equals sine squared theta, and we're done. For this particular one, I want to show you an alternate way to do this particular problem, and I would encourage you to add it to your notes. It has to do with the strategy here that we talked about, where we, here it is, create a monomial denominator, or we split apart into two where we have a monomial denominator. And so let me show you what I mean by that. Get rid of all this. All right, so here, and this is why we sometimes want to create a monomial denominator. We have a monomial denominator, so it's a common denominator for secant squared and for the minus 1. So we can split it apart, and this would become secant squared theta over the common denominator of secant squared theta. And this would be, we have minus, our minus here becomes our operation here, and then we have 1 over the common denominator of secant squared theta. Again, I'm going to leave sine squared theta alone. So anything divided by itself is 1. Secant squared, secant is the reciprocal of cosine, so secant squared, when I flip it over, becomes cosine squared theta. And our Pythagorean identity says 1 minus cosine squared is sine squared. And so this way, it's a little shorter. So that's what I mean by, sometimes there's often more than one way that we can do these particular types of problems. Some ways are shorter than others. All right, I think we have a practice problem here. Yeah, so why don't you pause the video, see what you can do with this one, and come on back when you're ready to take a look at what I have. All right, let's take a look at what I've got here. So first off, using the Pythagorean identity on the, sorry about that. For some reason it collapsed on me. There we go. So sine squared plus cosine squared is in the Pythagorean identity is equal to 1. So it was replaced with 1. And then this is a product of cosine squared and secant squared. So we can separate this into the product of two fractions. So this would be like 1 times 1 is 1. Cosine squared times secant squared would be that denominator there. And then what we have is the reciprocal of secant squared is cosine squared. So if I flip this one over, it becomes its reciprocal of cosine squared theta, and has a denominator of 1. Cosine squared divided by cosine squared, that reduces, and we get 1 equals 1. And once the left side is equal to the right side, that 1 was there all along, then we have verified the identity. All right, let's add this example. We'll do this one together. Notice our strategy here is to combine fractions. So that we're looking at this side over here, adding these fractions together. In order to add fractions, of course, we need a common denominator. And what's nice is that if you notice 1 minus sine alpha and 1 plus sine alpha, those are conjugates of each other. And so the common denominator would be their product. They don't have any common factors. And when we multiply conjugates together, we end up with a difference of 2 squares. So you can start to see where we're going. So we're going to take this one times 1 plus sine alpha over 1 plus sine alpha. And we are going to take the second expression times 1 minus sine alpha over 1 minus sine alpha. So now we still have our 2 secant squared alpha. That's our simpler side. We're just leaving as is. Here we're multiplying straight across. So we get 1 plus sine alpha. And when we multiply these together, distributing, we get a plus sine alpha and a minus sine alpha, which add to 0. And then we get a minus, and we have sine times sine, which gives us sine squared alpha. So we get 1 minus sine squared alpha. And then we have plus. And multiplying straight across here is going to give us 1 minus sine alpha over that common denominator of 1 minus sine squared alpha. Remember, we're only allowed to work with one side at a time, so I am still focusing on my right side here. But now I have a common denominator of 1 minus sine squared alpha. So I have 1 plus sine alpha from this numerator plus this numerator, 1 minus sine alpha. And here, positive sine alpha plus negative sine alpha, they add up to 0. So they're gone, and 1 plus 1 gives me 2. So now I have 2 over 1 minus sine squared alpha, alternate form of our Pythagorean identity. That is cosine squared alpha. And I still have my 2 secant squared alpha. So now this would be, I have my secant squared alpha. This would be 2 times 1 over cosine squared alpha. And the reciprocal of cosine is secant. So now I get, oops, I lost the 2 there. 2 secant squared alpha equals 2 secant squared alpha. And I'm done. All right, let's take a look at a practice problem. Here you go. Pause the video and try this one. It's similar. All right, let's take a look. So you can see it's very similar with our adding the fractions. We multiply by ratios of 1 to get the common denominator. It should be the product of 1 minus cosine beta and 1 plus cosine beta. That gives us 1 minus cosine squared beta as a common denominator. And 1 minus cosine squared beta in an alternate form of our Pythagorean identity is sine squared beta. And 2 divided by that is the same thing as 2 times 1 over. And our 1 over, since sine and cosecant are reciprocals, doing the reciprocal of that brings cosecant squared beta to the top. And now the two sides are equal. All right, let's take a look at this one. So here's another strategy. Sometimes when we have products such as 2 binomials times each other, we may want to distribute. Other times we may want to use this strategy first. Use identities before multiplying, especially if we have trig expressions that are squared plus or minus 1s, because those are very common to the Pythagorean identities. So we have a tangent squared plus 1 and a cosine squared minus 1. So let's take a look here. So if we go back to our Pythagorean identities, all the way back, here we go. We have a tangent squared plus 1 that is a secant squared theta, so we can do a direct substitution for that. We do not have a cosine squared minus 1, but an alternate form of this, remember, would be that sine squared equals 1 minus cosine squared. And this is the opposite if I take a negative 1 out of that, which means that what this would become would be negative sine squared. So what we're looking at back over here, going back to this example, here we go, almost there. There we go. So our tangent squared x plus 1 will become secant squared x. And our cosine squared minus 1, couple of different ways we can look at it, but one of the things we could do would be to factor out a -1 from this, and that would become then 1 minus cosine squared x. 1 minus cosine squared x from a Pythagorean identity becomes sine squared x. Right now we're just leaving this negative tan squared x alone. It's the simpler side. So we are also still using the strategy of transforming the more complicated side into the simpler side with another strategy added on to it. So our negative tangent squared x is just staying the way it is. So what I have now is the product of these three factors: secant squared, -1, and sine squared. So remember that secant is the reciprocal of cosine. So this, and I'm going to change the order, I'm going to move my -1 to the front. Secant squared can also be written as 1 over cosine squared. And sine squared you could look at as having a denominator of 1. Multiplying this straight across, that's sine squared over cosine squared. And remember that sine over cosine is tangent, so sine squared over cosine squared would be tangent squared. There it is. There's our negative tangent squared x. And so we have transformed the left side into the right side and verified the identity. All right, let's take a look at a practice problem that's similar. Pause your video here. Let's take a look at the result here. So we are looking at a direct application here of our Pythagorean identity on secant squared minus 1 is tangent squared of x. With our sine squared x minus 1, it's actually the opposite of our alternate form of our Pythagorean, so we can factor out -1 from this, creating this, and then our 1 minus sine squared becomes cosine squared. Tangent squared is sine squared over cosine squared, and then the cosine squareds will reduce to 1, and we get -1 times sine squared, and negative sine squared equals negative sine squared, and it is verified. All right, let's take a look at this one. So when things are not squared especially, so here we don't have any squared trig functions, a good go-to strategy is to convert everything into sines and cosines using the reciprocal and quotient identities. So here, what we are looking at is that tangent is sine over cosine times cosecant and sine are reciprocal, so that would be 1 over sine x. And we can actually leave secant x the way it is, or we could also transform it into its reciprocal, which is 1 over cosine of x. And it's a little faster to do it that way because now notice that our sine x factors will reduce, and we have 1 multiplying here straight across, we get 1 over cosine x. And so having transformed that, we're already at the left side equals the right side, and we are done. All right, let's try a practice problem. Pause here, give it a try. All right, let's see what the result is. Oops, did we go too far there? Yep, there it is. So here, our cotangent becomes, sorry about that, doesn't want to stay. Our cotangent becomes cosine over sine. Our secant becomes, try that again. All right, I'm just not going to touch the screen here. The secant becomes 1 over cosine, and then your cosines reduce, and your 1 over sine, this one, it was cosecant was left cosecant, and so 1 over sine became cosecant, it's reciprocal. If we'd changed cosecant x on the right side into 1 over sine, we could have been done at that second step. All right, let's see what else we got here. All right, here is another example that a good strategy to use is to convert to sines and cosines, especially because, again, we have none of our functions here squared. So Pythagorean identities are out in those cases. So here what we're looking at is tangent becomes sine x over cosine x, and cotangent is cosine x over sine x. Secant is the reciprocal of cosine, so it would be 1 over cosine x, and cosecant is a reciprocal of sine, so it would be 1 over sine x. Here you can probably start to see where we're going with this, perhaps, because here the denominator of individually are cosine and sine. Here, multiplying straight across, we get 1 over cosine times sine. And that will be our common denominator for this sum. So over here in the sum, what we're going to do is get our common denominator. So this one we're going to multiply by sine x over sine x. And this one we're going to multiply by cosine x over cosine x. And that's going to give us sine squared x over cosine times sine. And this one is going to give us cosine squared x over cosine times sine. And of course, if you wrote it sine times cosine, fine. Same difference with the multiplication operation. So now we have that common denominator, cosine times sine. And adding the numerators, we have sine squared plus cosine squared. And our Pythagorean identity says that sine squared plus cosine squared is 1. So one more little step here to replace that with 1. And now I have shown that the left and right sides are actually equivalent to each other, which is what we call verifying the identity. All right, let's see what's next. Here's a practice problem for you to try. Pause the video here, give this one a try. All right, let's take a look at the result. So this one, you can't change sine and cosine into anything other than themselves, but you can change cosecant and you can change cotangent if you want to. This one does not change cotangent, but you might have, which would be okay too. It would have given you cosine squared over sine of x, and your common denominator would have been sine. So here we're getting sine, common denominator for sine. Sine times sine gives us sine squared. Then we get 1 minus sine squared over that denominator of sine. And this part could have been cosine squared x over sine x. And then you'd be done at this step if you'd done that. Whereas in this problem, it didn't do that. So then it had to split it apart to get to cosine times cotangent. So it can actually be easier in many ways to change both sides into terms of both sines and cosines. All right, let's take a look at this one now. So new strategy here being used. We're going to multiply by a ratio of 1 using the conjugate. So here it's not about getting a common denominator because we don't have a sum or difference. It is about being able to get to a monomial denominator. So right now we have this 1 minus sine x. It's not a 1 minus sine squared, so we can't use Pythagorean identity. But we can create a situation where we can use a Pythagorean identity by multiplying this by its conjugate, not itself, its conjugate, 1 plus sine x as a ratio of 1. So here we're looking at distributing our cosine x. And so we're going to leave right now secant x plus tangent x alone. We could possibly change it, and maybe we will a little later, but I'm not going to right now. I'm going to see where this part goes. So distributing that, I get cosine x plus cosine x sine x. And 1 minus sine x times 1 plus sine x becomes 1 minus sine squared x. And using a Pythagorean identity, 1 minus sine squared x becomes cosine squared x. So in the first example, I showed you an alternate strategy towards simplifying that broke apart the ratio. So the cosine squared here is a common denominator of both of the terms in the numerator. So this is cosine x over cosine squared x plus cosine x sine x over the common denominator of cosine squared x. So these are power, here we've got powers of cosine that we can reduce. That would be 1 over cosine x. Here, powers of cosine can reduce, and that would be 1 over cosine, but we have a sine x then over cosine x. And here, I can either wait to transform my right side into my left side, or I can go, oh wait, cosine is 1 over, secant is 1 over cosine, and tangent is sine over cosine, and save myself a step. Left side equals right side, and so I am done. All right, let's try a Pythagorean, or probably a practice problem. Yep, practice problem here, pause. All right, let's take a look at the result. So here, the left side was left the same. You can, again, change it to if you want to, and then you'd be done at this step right here when the left side and the right side become the same. But otherwise, it's very similar. All right, here we go. There's another one. New strategy also with this problem. Working with each side separately. And we've actually already used this strategy. We're just emphasizing this strategy in this particular problem, where you use some identities to transform the left side and the right side until they become the same. So we have actually done this too, and we'll use other strategies also in this one. So one of the things that I'm looking at here is I have cotangent squared theta, and 1 plus cosecant of theta in that denominator. And I'm wondering if one of my Pythagorean identities might help me here. All right, so we have a Pythagorean identity that says that 1 plus cotangent squared equals cosecant squared. We have a cotangent squared, and so if I subtract 1 from both sides, then I get cotangent squared equals cosecant squared theta minus 1. So I can do a substitution here of replacing my cotangent squared with this from the Pythagorean, the alternate form of the Pythagorean identity. So I have cosecant squared theta minus 1 over 1 plus cosecant theta. Let's deal with this part first. So next off, I want to recognize this is a difference of two squares, and it can be factored then into two binomials. We'd have a cosecant theta plus 1 and a cosecant theta minus 1. I want to make it clear that with a sum, the order of the add-ins doesn't matter. So 1 plus cosecant theta is equivalent to cosecant theta plus 1. Not true with subtraction, is true with addition. So notice these are now common factors, and they will reduce to 1. So now on this side, I have cosecant theta minus 1. All right, let's now deal with the other side. So on the other side, what I notice is I have this monomial denominator. So this acts like a common denominator for both of the terms in the numerator. So splitting those apart gives me 1 over sine theta minus sine theta over sine theta. The reciprocal of sine is cosecant, so that is cosecant theta. And anything divided by itself is 1, so minus 1. And look at there. We have cosecant theta minus 1 equals cosecant theta minus 1. We have just verified the identity. All right, let's try practice. You can pause here, give it a try. Let's take a look. All right, so here's at least one way, using the Pythagorean identity on tangent squared, an alternate form anyways. Here, this is split apart, where 1 and cosine theta both have cosine theta here as their common denominator, so it splits this apart, well, maybe more like that. And then this is a difference of squares, so it factors into these two binomials. Secant theta plus 1 and 1 plus secant theta are equivalent because it's addition. So those reduce to 1. And the reciprocal of cosine is secant. Cosine divided by itself is 1. And so we get secant theta minus 1 equals secant theta minus 1. All right, that ends this lesson. And so give your assignments a try. And good luck. Have a great day.